All right, guys, welcome back. We are Game 2005. That's Game Physics in the fall 2021 semester at George Brown, and it's week 13, part 1, maybe the only part of our broadcast. Let's talk about a couple things where we're at today. First of all, we are at week 13. Earlier this week, the assignment 4, which is equivalent to assignment 3, part 2, that was released. And I posted it on Blackboard. I want to talk about that first. That's something we want to talk about. I also will want to talk about, kind of ideas for the starter and how we can modify the starter. If we have time, I'll do what I can to, to show you what I would start with. Because I know what the requirements are for the assignment. So let's get into that first. I'd like to try and look at assignment 3, part 2. Assignment 3, part 2 is the same partner groups as before, just to save time. I know there are always people that are like, I don't want that partner, but I've made it the same because to save time. I'm so sorry, guys. But I can make another group set. But what it's going to do, it's going to make you guys all sign up and re-sign up with this. I'm hoping that your partner that you've picked for assignment 3, part 1 is the right partner, because you're going to have to keep them. All right, so let's get into the stuff for what this is going to look like. One sec. As I pull up my details for this one. This is kind of really good. Okay, so this is kind of the most challenging of the assignments that we've given you this semester. And it kind of goes in line with what we talked about from, last year when we were doing AI, right? Always this is kind of a culmination of stuff that we've talked about. Okay, so again, this is group size 1 to 3. Assignment weight is 15% of your final grade. This is due for now, Friday, December 10th, 2021 at midnight. So 11:59 p.m. Toronto time. And again, what you're doing is you're building on assignment 3, part 1. So this is a 2-parter. This is the second part of a 2-part assignment. So again, this one is different. You're going to make a block, of towers, tower block, right? And or a block tower, and you're going to throw different size balls at the tower block, and in hopes that you're going to knock it over. That is the idea behind this one. Okay, so just wanted to go over the details with you about this first before we move on. So please, I'm hoping that you're going to, hello, Catherine. I'm hoping that you're going to have questions for me so I can answer them, because I want to make sure that we're clear. Okay, so using a series of C# scripts in Unity, build on your existing framework to model realistic momentum, conserving collision responses and friction with sphere to plane, sphere to ABB, and ABB to ABB types of interactions. So more interactions than the last assignment. So different kinds. You've done sphere, and sphere plane, and I know that Joss is going to be working with you on sphere ABB and ABB interactions. That's good. That's like what that means, overlap. Then this is the instructions. Then you're going to create a game with a stack of small AABB type blocks. There you go. Right. And on top of a larger box. Okay. Or it could be an enclosed area. It's really up to you. I recommend we keep the box that we had last time, kind of like a box that's in there. And what you want to do is you want to throw a ball. So you're going to use the fly camera, the camera controls that we already developed, and you're going to basically throw a ball from the camera towards the blocks. That's how it's going to go, all right? And players can choose what kind of ball to throw, from at least a ping pong ball, a baseball, a basketball, a bowling ball. We made some basic spheres. You're going to expand on these spheres, and you're going to give them different properties, okay? So we'll talk about that in a sec. Each type of ball should have an appropriate size and physical properties. For example, the ping pong ball should be very bouncy and weigh only 2 to 3 grams. The baseball should not be very bouncy and weigh about 150 grams. And the basketball should be very bouncy and weigh about 625 grams. And the bowling ball should be slightly bouncy and weigh about 5 kilograms. And we've given you a little bit of a table that shows the things that you want to know. So a couple things are the wooden block, Aabb. It's going to have, every object is now going to have a material, a physic material that you're going to create on your own, right? So one of them is going to be mass. Then there's going to be, mass will be part of the rigid body. Bounciness and friction is going to be part of their, almost like a material that's going to be that they're made of. Normally what we call it in Unity is a physic material or a physics material. Okay, and bounciness means this works out to be the coefficient of restitution that Joss will be talking about with you in lab. And friction, think about this as something that is going to reduce your momentum and impulse, right? So when you have friction on a surface and let's say a ball hits the surface with friction, that means you're going to have, it's going to take away from that perfectly elastic collision that I would normally have, especially with bounciness like this. If I put my bounciness as 0, that means there's no bounce. It'll just like stick. That's what it'll do. It'll just, stick onto the wall, right? But it'll fall down because of gravity. That's what bounciness will do. Now, if we had no friction, that means it would slide and there would be no energy loss really at the end of the day, right? Or very little. If the friction was very low. If the friction is very high, then you're going to get some energy loss, which means because the friction is going to slow you down. Think about the friction as kinetic friction or dynamic friction. That's what it's going to be, right? As it hits a surface. Okay, so that's what it's going to be. And you can see that there's different properties, variable properties we put in this little table to give you some variations. All right, so that's what we want. Finally, you're going to create a short video demonstration, 5 to 10 minutes with your favorite screen capture streaming tool. Show the simulation working with all of its features. Please do that. Describe the system architecture showing relevant code and objects and how they are connected. Show how to add and edit new physics objects using your system. If possible, demonstrate the robustness and limitations of the system by tweaking and stressing the simulation and discuss the shortcomings. All right, so similar to what you did in assignment 3, part 1. Now you're going to add a few more things. So here's a feature. Feature number 1. Aabb, collision detection and response. So that's worth 20% just to be able to get that right. And you're doing some of this already in lab, so it shouldn't be like undoable. Developers can designate an object to be treated physically as a solid axis-aligned, non-rotating box. Boxes can interact with spheres and other boxes with rigid collisions. Okay, so that's what happens. So that's the first thing. The first part, I think, is this is an easy one to get. Here's another one that's not as easy. A momentum conserving collision response system. You already have some repositioning that you've done, but you've never done a bounce. Now you're actually going to do the bounce that we talked about last time. So developers can designate objects to have different levels of bounciness, or we can call them the coefficient of restitution, so that collision response between different types of objects may have different coefficients of restitution. So if I have two objects and they have two different kinds of coefficients of restitution or bounciness, then what you want to do is you want to average those out. That's what we're going to ask you to do. So if I, for example, if I have the ball that I'm throwing has a bit of friction on it as well. Let's say it's made of leather, and you have a wall that's made of some kind of rough material. Let's say a rubber wall or something like that, or maybe something that's made of rough, rusted wall. Let's say something like that. There's going to have you're going to have some kind of coefficient of restitution on the wall. Plus, you're going to have some kind of coefficient of coefficient of restitution. Coefficient of restitution on the on this leather ball. Let's say as an example. And those two things are going to average out to give you an average bounciness, right? So we're not going to add them typically, okay? We want to average them. Now again, Joss will talk about this, so he'll discuss how those things are going to be done. Allow collision response to take into account momentum and conservation of momentum. When objects collide, they apply impulse to each other based on classical Newtonian physics. So in other words, if I have energy that I'm using. The energy is being transferred to the ball in terms of its velocity. Once we have velocity, we have some kind of kinetic energy. Remember, the amount of kinetic energy we have in an object, right, which can either be created or destroyed. Remember this from a conservation of momentum perspective is this, that the kinetic energy is equal to 1/2 mv squared, mass times velocity squared. So that is the equation you could use for, for kinetic energy. And then you can, kind of extrapolate that for momentum, which is very close to what kinetic energy looks like. So you take that energy, and then what you want to do is transfer that energy, right, to other objects. Let's say if two objects hit each other and one has energy, the other one is not, that situation where the object is stopped, and there's different cases that I talked about a couple of slide decks ago. One of them was if you have a very massive object and a very small object, and the massive object hits a smaller object, then the smaller object gets twice as fast, right? That's what happens, right? And so on. So please take a look at those things we talked about over the last few slide decks that we were using for momentum. And then what happens is if you hit if it's perfectly bouncy, if like you have very, very high coefficients of restitution, then what's going to happen is you're going to have a perfectly elastic collision if you modify the stuff in our little UI to add some properties to allow you to dial up the restitution or dial down the restitution for different objects or all objects. You can make it so it's very, very bouncy. It should work with sphere to sphere, sphere to plane, sphere ABB, and ABB type collision detection. So this is what the restitution will work like. It won't work with a you can see that this is all the different types of collision responses we want, okay? Okay, that's number one. So that is 2. This is worth 20, but I think this can be quite challenging to put together. Next, the friction system. So collision response, now friction. So developers can designate an object to have a physical surface material, rubber, plastic, leather, like we said before. It may have different coefficients of static and kinetic friction. Simulate friction between objects and surfaces when they rub against each other. Different combinations of materials may have different coefficients of friction between them. Should work with sphere to sphere, sphere to plane, sphere ABB, ABB interactions, same as these ones. So you have friction and you have restitution. That's the response, how much bounciness there is away from each other, as well as when you hit, what happens? Well, you slow things down, you lose some energy here, right, with this as well. So those are the 3 systems. One of them is a detection and response system. So, again, you want to, kind of do this is really the repositioning piece. So where you collide and reposition. That's what happened. You got that from your last assignment for the most part. So this is easier to do. These parts are harder. Friction is definitely more difficult because you need to do some kind of averaging. As an example, you can always look at what Unity does for its friction system in 3D as well. We'll talk about that in a bit. Code quality, I'm also looking for things like helpful names, comments, organization, use of white space, systems are scalable, good performance, avoids hard-coded relationships or magic numbers. So you expose some of these things on the inspector, regular things that we're looking for. Finally, your demonstration. We want you to demonstrate it nicely. So that'll be your video and how we can hear you and everything else. And so explain well, demonstrating good understanding, but, don't read every code line by line. That doesn't help us to make sure that you understand what it does. Show robustness of the simulation. So actually try and modify some values so that way you can show that your simulation is not going to fail based on higher values that you're going to use for your numbers. For example, higher masses, increased speed, all kinds of other stuff that you're going to do. More restitution, less restitution, more friction, less friction between objects, and so on. Show how to add new physics objects using the system. Discuss major challenges and limitations of the project. Video must have sufficient quality to have legible text and clear audio. Notes, the simulation does not need to support rotating, rolling, or angular momentum because that's going to be something that you're going to cover in the next physics course, okay? The simulation should not include air resistance or drag, so we can assume that there is none. Collision between pairs of objects not specified, example, ABB and plane, are not needed. So, as an example, we haven't talked about ABB plane, but it's not required, but if you want to put it in, it's up to you. We haven't asked you for it. If you choose to implement features not specified like those mentioned above, please mention them as extra features. If added, they must be physically correct. or at least feel physically correct. So if you add air resistance, then, okay, fine, make sure that it works properly. In the video demonstration, you do not need to read all the code line by line, like we said, and the balls do not need to look lifelike, but it should be obvious which is which. In other words, try and grab some textures. Yes, it's being recorded. Try and grab some textures that are realistic. So grab a baseball texture, a basketball texture, different kinds of textures, and put them in. So that way you have everything you need. To submit, all right, your video itself, maximum 10 minutes. Again, at the start of the video, you should have a title card or slide in the video, including a current image of all the group members and your name, student numbers, and so on. Video must have sufficient quality to have legible text and clear audio. Must match the project submission exactly. So don't submit a video and then update your project and it's totally different, okay? Or vice versa. Must match the video exactly, your project submission, so both must match. The project must run in Unity 2021 1.19F1 on Windows. Submit a link to your private GitHub repository containing the entire Unity project and source code and a zip archive of your entire Unity project and source code. These are backups of each other. Project constraints. Purpose of the assignment is to understand classical physics and physics systems and games. Unity is permitted to use this assignment purely for rendering 3D shapes as an alternative to writing your own 3D engine and render. You are not permitted to use the following: Unity's physics engines. This is all the same stuff as last time. Anything from Unity's physics API, any physics plugins, scripting plugins from third-party sources, Unity rigid body components, 3D and 2D, Unity collider components, ray casting or line casting, any other pre-existing component script or system that provides physics, simulations, collision detection, and collision responses. Using any of the things that we talked about here will net you a 0 for this thing. And we have a little bit of a rubric of where we're looking to get that stuff done. So I think this is pretty comprehensive. It's a little bit more difficult, I would say, than the last assignment, but the idea is pretty good in terms of what we're asking for. Any questions related to this assignment, assignment 3, part 2, before we move on? So that is your assignment details. Nothing yet. Okay, good. If you do have details, then we're going to look at if we are a group of 2, can we assign a third for this one and add? Yes, you can. Yeah. Just got to let me know, and I can remove them from one group and put them into the other group. Okay. So make sure you do that with me, Samuel. All right, so thank you for that. That is your assignment 3, part 2. Hopefully you're going to have fun with that one. I think there's a lot of learnings here for assignment 3, part 2. It talks about collision response systems, and you're going to be set up nicely for physics part 2 or physics number 2, which is going to happen next semester, right? So the next course in line with this one, which you'll be also using Unity, which is a really good thing. So really nice kind of connection between one system and another. On that, let's continue now with what we want to talk about today. We're going to quickly review 3D collision detection, again, just to make sure we covered it from last week. 3D collision response, we're going to be talking about something called manifolds and impulses. And we're going to do a Unity demo, but the Unity demo that we're going to be doing is I'm going to show you, kind of a starter that I've put together for you guys that allows you to launch stuff from the... You'll be continue developing physics engines. Yes, you will, in another course. We'll do a little bit of a starter there. Okay, let's continue with this stuff. So let's revisit our 3D collision detection. So one thing we talked about, as with 2D collision detection, axis-aligned bounding boxes, AABBs, are the quickest algorithm to determine whether the two game entities are overlapping or not, right? In many ways, well, them and I would say spheres are pretty much the same. And this consists of wrapping game entities in a non-rotated and thus axis-aligned box and checking the positions of these boxes in the 3D coordinate space to see if they are overlapping. Okay, so that's what we're doing. We're doing overlaps with AABBs, right? And the axis-aligned constraint is there because of performance reasons. That's what we want to do. So the overlapping area between two non-rotated boxes can be checked with comparisons alone, whereas rotated boxes require additional trig operations, which are way slower to calculate. And that's why we want to try and avoid them, okay, as much as possible. If you have entities that will be rotating, you can either modify the dimensions of the bounding box, like so it still wraps the object, or opt to use another bounding geometry type, such as spheres, which are invariant to rotation. We don't care if it rotates, if it's something that's spherical, right? And the animated GIF below shows a graphic example of an AABB that adapts its size to fit the rotating entity. So this is something you could probably do as well if you have something that's moving. Okay, now again, we don't care about rotations for you, but if you wanted to simulate some kind of rotation, you could do it by using this bounding box. The box constantly changes dimensions to snugly fit the entity contained inside. Okay, that's what it does. And so what it does is it creates a cleaner looking collision, right? Even though the entity seems to be very irregularly shaped. So again, we talked about point versus AABB. So is the point inside an AABB? We talked about that. That is a pretty simple calculation. And we need to check whether the point's coordinates fall inside, and we can consider each axis separately. And that's how you do, that's the first part of doing AABB type collision detection. We talked about that. And here's the next one. We want to say we have an intersect method where we intersect one AABB with another. Okay, this is the formula for that. So we just need to do one test per axis, and then that way we'll get we can check to see if they're colliding. It's pretty simple. Point versus sphere, we can do the same thing as the point inside a sphere. We talked about this last time. And sphere versus sphere, well, we have two spheres. We're going to check if the distance between the centers are less than the radius combined. All right, that's what we're checking here. And of course, what we want to do with, instead of using math.square root, you can use something else, like, for example, squared radius and squared magnitude, which is kind of less computationally expensive than what we've seen before. All right, sphere versus AABB, this is new. Again, for you guys, the same thing that you've seen last time, but it's like you have a sphere and a box, and then you kind of make a comparison, and you get, do I overlap or not? These are the, I'm mentioning this because these are an additional set of code fragments that you might use in your code to help you if you can't do it, you know, kind of in a lab, or you need additional, you want to do something different than what was shown. Now, we've talked about those things. That's awesome. But what about what we talked about last day? We said that, you know, collision detection is pretty lousy if we're doing it from every object to every other object, right? And sometimes we want to create more complex, you know, kind of collisions and overlaps between two different objects. And so what we call these things is we can have something called bounding volume hierarchies, which are BVH. BVHs, or bounding volume hierarchies, are, example is, if I have the scene itself, that's the top of the hierarchy. I have a tank inside the scene. So there's my, let's bring this, maybe I can make this a little bigger for you guys to see. There we go. So the tank is inside the scene, and it has a bounding volume for the entire tank. But inside the tank, there is a turret with its own bounding volume. That is a bounding volume hierarchy, because the tank is got a bounding volume on the outside, and there's a bounding volume on the inside. Okay, and you can also see that the bounding volume on the inside, you might even have another one for not just the turret itself, but the gun could be separate itself, right? That part, which is very different. So now I have 3 AABBs as opposed to 2, or 1, I mean. Here's another one. We have some kind of hover vehicle, same kind of tank, right, like we had before. And instead of using AABBs, we use spheres. So we have a sphere on the outside, and then what you have is several spheres on the inside, and the spheres on the outside are the first line of defense. So we say, okay, so it's something that's collided with the tank itself, like the outside of the tank. And then what about, did it collide with the inside, right? If it's already passed through this first area, now we're going to start checking the second area. But we're not going to check this top part at all until it's past the first area itself. Okay, so things to note about that. So it's kind of a way, another way that we've talked about, which is an optimization, right? To make sure that, you know, we don't have, and this is, the idea here is we talked last week very briefly and very casually about something called spatial partitioning, okay? And we're going to kind of talk more about that. So here's a more complex example. We have a robot, right? And the robot itself has a bounding volume. And inside the robot, there's several other bounding volumes that are associated with the head, chest, arm, and so on, okay? And so this more complex bounding volume hierarchy, the great thing about this is we can adjust this to have a better performance. Collision detection can also be implemented as a several stage process and can be further developed into an engine that can be integrated with game logic and render engines. So the way it would work is you have your game update loop, whatever that is, and then you have your draw loop down here in the bottom, right? Now if I was going to do it with SDL2, we could literally have those things happening. And in between, you would have your collision system stages. So the first one would be sweep and prune. That's the first stage, right? Sweep and prune is process bounding volume hierarchies and other approximations. That's the first part. So what are the bounding volume hierarchies? Almost like in a tree-like structure. And then number 2 would be object collision detection, process final primitives, and compute intersections. So of the things that are actually colliding. And then we have our collision response system, which is correct for interpenetrations and deform geometry if required. So this is more of a holistic approach to looking at it, okay? So that's your collision engine design. So let's think about that while we're talking about collision response for 3D. Similar to what we've talked about so far in 2D, right? In 3D games, they behave similarly to what they do in real world. We detect a few things. We detect interpenetration and model contact. There's two pieces there. Interpenetration means overlap. Model contact is when an outer part of a model is touching another outer part of a model. That's different, okay? We want to ensure that objects react accordingly, to believable dynamics. So again, we want to maintain or preserve momentum, right? Conserve momentum. And we want to enforce non-interpenetration. So we won't allow objects to sit inside other objects. That's not allowed, okay? So due to discrete time steps, and discrete means we have one frame and another frame and another frame, right? The instant of collision or point of discontinuity is not always obvious, right? For accurate calculations, we need the exact collision time, or at least correct within a certain threshold, some kind of delta time that we have, right? So again, we have two objects, one object that's moving in this direction, it hits the other object, but we want to know where the other object, when the other object hit, not just where, but when, right? Once we know when it hit, when it should have hit, which frame or which part of a frame it should have hit, as an example, then what we want to do is we want to backtrack to where it would have hit, right, and move it out. Okay, so this is, again, T0 plus delta time, T0 being start time, plus some kind of delta time. Some time has elapsed where we're checking, right? And then what we want to do is the time of collision. We want to know when the exact time of collision would have been, okay? So what we want is, here's something about retroactive detection, or also known as backtracking. So we want to wait for an interpenetration or an overlap is what we want to say, right? And then step backwards in simulation time and redo the collision detection to find the time of impact. So again, imagine where a sphere is colliding with a plane, as an example, and it has gone through because of the discrete time steps that we're using in our collision system, right? Discrete time steps, one frame, another frame, and so on. Or we check every X number of frames, however it is, or the speed. We're moving at a certain speed as well, every frame. And we want to say that, okay, well, if it's penetrated, so if it's gone through this thing, we've detected that it's been penetrated. Well, we want to move it back to the position where it actually collided. All right, we want to kind of do some backtracking. In order to respond to collisions, we must first know something about the collisions. And to learn more about the features of collisions, we start this by developing something called a collision manifold, which is actually a different level of detail than what we've talked about so far. And it'll hold information about the collisions. After we create manifolds, we build a linear impulse system to learn the basics of collision resolution. Resolution is another term for response. Okay. So pretty straightforward. And again, what we want to let's talk about manifold for spheres first. In order to resolve collisions between objects that have volume, we need to learn about the nature of the mentioned collisions. And the additional information is known as the collision manifold. And a typical collision manifold usually contains the following things: collision normal, so that to me is the angle of attack, or the angle of collision between the two objects. Some kind of penetration distance, how far they've interpenetrated, right? And a set of contact points, the place where we want to reposition them to, right? Additionally, a manifold might also contain the following things: references to the colliding objects, so which objects collided, right? The relative velocity of the collision, we're going to talk about relative velocity, and the nature of the collision. No collision, colliding, or penetrating. Which type are you? Because there's one of those. You didn't have a collision, they passed by each other, no collision. They collided, or they penetrated. If they penetrated, we need to reposition. Okay, because sometimes we can have a perfect collision. It kind of happens at the right moment, and we catch it before it penetrates. Okay, rare, but it can happen. So let's assume that we have two colliding objects, A and B, and the collision normal of the manifold between the two tells us what direction each object needs to move in to resolve the collision. So if A moves in the negative direction and B moves in the positive direction, the objects will no longer intersect. So let's take a look at what that means. So if I was going to draw these two things, I have two spheres, and let's just draw them as circles for now, right? Let's draw them as circles. So we have one circle. Let's suppose this circle is A, and we'll have another circle, and that circle is B, right? Didn't quite draw it the right way. Let's do it again. This circle is B. There we go. We have an interpenetration. And what we want to do is we want to have a line that goes between the two centers. That line is the normal that we talked about before. That's part of our manifold. So we kind of draw a line. Draw a line. Come on. We draw a line between the centers, right, as an example. So the line between the centers is the normal, right? So we do that. Why? Because, well, if this is moving in a direction and the other thing is moving in another direction, we need to reposition them along this normal regardless, okay? So that's the first thing we can do. All right, so let's continue. So the penetration distance of the manifold is half of the total length of the penetration. So again, we want to think about, I have a manifold, my collision manifold, and I want to figure out the penetration distance. We take the total penetration, the length of the penetration for both, and we put it in half, which means that's how much I'm going to reposition my object, like we've talked about before. Each object needs to move by the penetration distance, and it's going to be different for each object, depending on its speed, to resolve the collision. Finally, the set of contact points in the manifold are all the points at which the two objects collide, projected onto a plane. All right, that's what we want. And the plane these points are projected onto has the normal of the collision normal and is located halfway between the colliding objects. So almost like we're doing SAT, right? Or separating axis theorem. So we will start by building collision manifolds for a pair of spheres. And the nice thing about spheres is they only have one contact point between them, right? So here's the contact point right in the middle. And what we want to do is we want to reposition them. Here's the penetration depth. Right, here's the total penetration, right? And we want to move the big sphere to the left and the small sphere to the right. And that's what we want to do. In the collision normal, it shows us if only one sphere was moving, we can kind of create a normal, and this is a head-on collision between one sphere and another. So that's the collision normal. So we have some information that we can put into the collision manifold. So to find the collision manifold of two spheres, we first find the combined radius of the spheres. That's the first thing we do. And we then, if there's a collision between the spheres, the normal of the collision is a normalized vector that points from sphere A to sphere B, whatever sphere A and sphere B is. And you saw the big sphere and a small sphere in that diagram. And the penetration distance is half of the distance between the two spheres minus the combined radius of the spheres. So that's what you can do to figure that part out, okay? So again, we have B radius and we have A radius. This is A radius, and you can see that the collision normal goes from the center of one to the center of the other, right? And we're normalizing it. So when we say normal, we have the unit vector, so a unit length of 1 or magnitude of 1. And then when we want to find the magnitude, right, as an example, this piece here, the magnitude of overlap, if you will, or the total distance, overlapping distance, we take the A position minus B position minus A radius plus B radius, and we get this number. Okay, that's the number we know that we've penetrated. That's the penetration distance. All right, so if we're looking at an oriented bounding box in a sphere, we first need to find the closest point on the oriented bounding box to the sphere. Now, we haven't talked about oriented bounding boxes. Remember, we said that oriented bounding boxes are more expensive. We have to do more trig calculations than we normally do for an AABB, but it's nice to actually mention what they are anyway, so you understand the complexity, right? So we have several conditions here. So the penetration depth will be half the distance between these 2 points. We have a point on the sphere, right? And we have the collision normal, and that's the closest point on the box to the sphere itself. So we have that information, and the penetration depth is, right here. And you can see that we want to move the sphere and the OBB, so the kind of object aligned bounding box back along the collision normal. That's what we want to do. Okay. So when it comes to regular boxes, though, so again, finding collision manifold between two OBBs is difficult, but the collision normal and penetration distance come right from the separating axis theorem. And there are potentially, and here's one that's really interesting for me, right? This is for your interest, is there's 15 axes of potential separation between two OOBBs. So that's where the difference is between AABBs and OOBBs, right? While performing the SAT test, we keep track of which axis had the least penetration, and that is the axis of intersection. Okay, so that's how we have to think about it. The collision normal is the same as the axis of intersection. All right, so that's the other thing we have to know. And the penetration depth is the difference between the centers of the both OOBBs projected onto this axis, like that axis was a plane. So when we look at them, we can see that these are some examples of where an OOBB, contacts with another OOBB, right? So we can have point and face, edge to edge contact, edge to face contact, face to face contact, point to edge contact, point to point contact, and here's another type of face to face contact, right? And so that is very interesting that you have all these different things, but it becomes complex. And like I said, we're talking about it, but don't expect you to do something like this. This is if you had rotating boxes, and we're not expecting you to do any kind of rotating boxes. All your boxes in assignment 3 part 2 are supposed to be non-rotating because it's so hard to do. Okay. So again, so there is a less than optimal and simple solution we can implement. Given two OBBs, A and B, we will find the intersection points of edges A and the planes of B, as well as the edge of B and the planes of A. And this essentially clips each box against the other. And the resulting contact set will contain duplicates or extra points, but it will provide a reliable manifest, which is pretty cool. All right, so that's what you can do. So that is some examples of more complex collisions than we've seen in the past. And again, this is part of your collision manifold. And again, your collision manifold is much easier because all you care about is simple collision detection and responses. Okay. So let's go on to linear impulse. So when we're thinking about collisions, we use impulses, right? Remember that an impulse is an instantaneous change in velocity, right? And when two objects intersect, we will find the collision manifold between the objects. So now we find the point of intersection, the depth of penetration, and also the collision normal, which is what we want. And we want to figure out what impulse will resolve the collision. So I have some kind of impulse that's coming from box B to box A and from box A to box B. And we're going to be able to separate them based on this impulse. Once we have the features of a collision, we apply a linear impulse to colliding objects to solve the collision. And to make the physics more realistic, we also must apply some friction, which is what we're talking about in assignment 3, part 2. Okay, so in order to find the linear impulse needed to resolve a collision, we have to find something called the relative velocity of the colliding objects. What is relative velocity? It's the difference between the velocity of rigid body A and rigid body B, right? So rigid body B is always considered to be resting. It's an easier way to think of it that way, okay? We can find the relative velocity by subtracting the velocity vectors as illustrated. So relative velocity is equal to velocity B minus velocity A, okay? Whatever that is. All right, and next we want to know the magnitude of the relative velocity in the direction of the collision normal. So now that we have the relative velocity, we want to kind of calculate, modify that, or kind of multiply the relative velocity by the collision normal, and we know how large that vector of impulse is, if you think about it, right? If this magnitude is greater than 0, the objects are moving away from each other and we can't apply any impulse. They're going in the opposite direction. We find this magnitude by taking the dot product of the relative velocity and the relative normal, okay? And the relative normal is just the collision normal. That's what we just call it, the relative normal, all right? So we want to take the dot product of these two things. And, okay, so that's the first thing. So once we know that, we found the relative velocity, and we figure out what is the magnitude that we're talking about, the magnitude of the relative velocity. Once we figure this out, and we know that it's not, it's greater than 0, so there's some kind of magnitude, right? That means they're moving away from each other. But if it's less than 0, we know that it's going to tell us that they're moving towards each other. Okay, that's what it means. All right, bounciness of objects, we also call this the coefficient of restitution, is based on how elastic. We talked about elastic and non-elastic type of collisions. There's 4 types we talked about. One is perfectly elastic. The other one is perfectly inelastic. One is simply elastic, and the other one is simply inelastic. So can anyone tell me, if you're watching, what's the difference between an elastic and a perfectly elastic collision? What's the difference? Because people get always confused about that. Because that's the first thing I'd like to ask you guys. Elastic, and the difference between elastic and perfectly elastic. Good. Sam says perfect has no energy loss. That's good. Okay, what about perfectly inelastic? What does that mean when we have something that's perfectly inelastic? What are one of the features of something that's perfectly inelastic? There's a feature that we always talk about. Loses all energy, yeah, okay. But what about both lose the same energy? Okay, what about both masses combined? When we have a perfectly inelastic collision, both masses combine together to make a mass, and they move together after that. They stick together. That's one thing that happens with perfectly inelastic type collisions. All right, perfectly inelastic collisions happen when the momentum is not conserved, because what happens is they stick together. They kind of become one. And we remember that a couple of slide decks ago, we had an example of, we had a truck and another truck. They kind of hit together and then they move together along another axis. That's a perfectly inelastic type of collision. So we can say that the bounciness is how elastic they are, how bouncy they are. We can use something called the coefficient of restitution to model bounciness. Coefficient of restitution will be represented by E in our formula, and both the objects involved in the collision have a coefficient of restitution. We will use similar value as the coefficient for collision. So we say that we want to take, and it says min, right? But here's the coefficient of restitution, or elasticity. That's why it's probably E. And we want to take the minimum value between A and B, 2 different objects. The magnitude of the velocity of an object after a collision is the same as the magnitude of the velocity before the collision, all right? Scaled by the coefficient of restitution. So in other words, if we have some kind of velocity, the magnitude of the velocity of the 2 objects, we want to multiply the relative velocity times the normal, which is the collision normal, by the coefficient of restitution to have a reduced value, if you will, when it comes to this bounce. So it kind of goes in the opposite direction. That's why it's negative. Whatever the direction was for the vector, now it becomes the other way, right? Kind of bounces in the other way across the collision normal, right? And we use the negative coefficient of restitution before because after v prime is pointing in the opposite direction of v. So v, we had a velocity that was going in one way, and now we're bouncing back the other way, right? So this magnitude will be used as part of the magnitude of the impulse j. Okay, so now that we know those things, impulse is defined as mass times velocity, right? mv, that's impulse. Therefore, velocity equals impulse, right? Divided by mass. We're just moving things around. So if I was going to say what velocity is, we can say that we take the impulse and divide it by mass times the normal across the collision normal, right? As an example. So v prime, the new velocity that you're going to have, is the initial velocity plus the impulse over the mass, right, times the collision normal. Okay. So that is how we look at everything, right? And we also need to adjust the value of the coefficient of restitution because there are two objects involved in the collision, right? We have collision object 1 and object 2, and that is going to change the way things work. We take the first object, we invert its mass, 1 over mass of A, the object A, plus 1 over mass of B. So we now have a different mass than we had before. Okay, and what this has done is we've reworked the formula to calculate what linear impulse is. That's what J is. Okay, which is -1 plus the elasticity, which we're going to get, right, times the relative velocity, dotted with the. Remember, we want to find the magnitude. This is the magnitude, so we have that dot in there. That's the dot product between. That's the magnitude of the relative velocity. So we take the magnitude of the relative velocity multiplied by 1 plus the elasticity, that value, the negative value of that, and divide it by the masses, one in the inverted masses, to get what the impulse is. It's a number that we're going to get, right? And that impulse is going to give us the energy that we need to maintain or destroy, depending on what we have, right? Finally, we can update the velocities of objects A and B. These objects must move in the opposite directions to resolve the collision. We assume that A is moving and B is resting always, right? And therefore, we want to move A in the negative direction of the collision normal and B in the positive direction, right? That's how it goes. So one goes one way, the other one goes the other way, across the collision normal. So it's not, remember, it's not across an axis. It's whatever that collision normal is. And we found the collision normal because we kind of decided where when we put together our manifest, what that is. It's kind of, a line that draws from the center of mass of each of the objects. All right, so, and then we can find the velocity, so this is v prime, right? Which is, when we say v prime, it's like, this is velocity initial, and this is velocity final. So this velocity initial of B, this is velocity final of B, and velocity would be a vector. Okay. So once we have this, and we take the impulse that we calculated already between the two objects, and then we use this formula here to figure out the final velocity for both. Okay, so that's the way to figure it out. For the most part, because remember, it's relative velocity that we're trying to figure out, relative velocity. Now, this is minus friction. If one had more friction than the other one, if one had more restitution than the other one, then you're going to see one had a bigger mass than the other one, right? That's going to change the velocities, right? All right, so again, so we have one thing, which is bounciness, and that's one impulse, right? And we have a separate impulse for friction. That's a separate thing altogether, all right? So friction is applied as separate impulse. We apply impulse friction after applying the constraint impulse that keeps objects from penetrating. All right, so we do that as well. So we kind of move them apart. Impulse has a magnitude of J moving in the direction of the collision normal, right? And friction will be applied in a direction tangent to the normal, right? So whatever the normal is, it's going to be tangent to it, okay? Which is interesting. So tangential kind of energy that's happening. And we call this direction T. Similarly, the magnitude of the friction will be called JT. J is the direction of the collision normal. So the magnitude of J, right, impulse, right, moving in the direction of the collision normal. So then when we find the tangent vector, the way to do that is we take, to find T, we get the relative velocity of both objects minus the magnitude of the relative velocity. That's what VR dot n is, times the collision normal again. So we do this, that is the tangential vector, right? That's the area that it's going to, where the impulse, the friction impulse is going to apply. Once we have the tangent vector, we find the magnitude of the friction by substituting T into the formula for the magnitude of the impulse. So again, it's very similar to what we did before. So instead of doing the magnitude that we have before, instead of the normal, remember the normal was here before, relative velocity dot the normal. Now your relative velocity dotting across the tangent, right, vector. And now we're going to get the new term, JT. So impulse across the tangent. Okay. And finally, once we have that, the magnitude of the friction can never be greater than or smaller than J, scaled by the coefficient of friction. All right. So we can say that total friction is the square root of friction A and friction B. Right. Those are the things that we want to do. And the impulse across the tangent is equal to the maximum of JT and a negative impulse times the friction that we're getting, the total friction that we're getting, the square root of those two things added together, right? When we say square root A and B, we're adding them, okay? And then again, we get the maximum. That's what this is. And then we do the minimum on this as well. And then what we're going to get is the proper magnitude of friction. So again, this is the exact way of doing it, right? Joss is going to show you another way of calculating the coefficient of friction. One thing to note is that whenever we look, we always want to model after something that already exists. So when we go back to Unity, if I was going to look at Unity's Physic Material, right? There's two. There's a Physic Material and there's a Physic Material 2D. The Physic Material looks something that looks like this, where we have dynamic friction, 0.6, or some other value, static friction, bounciness, which is your coefficient of restitution, and then what do you do with those things, right? So Unity describes what they do. They kind of you can choose how to combine the two objects together. For example, if I have two materials and they interact, so I have a dynamic friction of one that's 0.6 and another one that's 0.4, then the average dynamic friction is going to be 0.5, and that's what we use, okay? Same thing with bounce. When I have two bounciness that combines, so I have a bounce that's, let's say, 0.1, another one that's 0.3, then the average would be 0.2. That's how we calculate the total bounce. And the reason why we do this is because this is a fast approximation of what would happen. It's not 100% accurate. And it talks about how to do that here, okay? But you can see that there's different ways of combining that Unity would do it in their own physics engine. They do things like either averaging, the minimum, the maximum, or we multiply, okay? So it really depends on what the effect is that you want. Okay, and it talks about all of that right here. So this is Unity's documentation. And if we know that Unity does something like this, this is something to strive for. Your system should look something that looks like this for assignment 3, part 2, where you can adjust the dynamic friction, the static friction, and the bounciness, as well as how they combine, right, for each object, And that way, if you have this, then you're going to be able to calculate once I have these values, friction values and bounciness values, I have them, then I can use the formulas I just applied for you to calculate impulse. And there's other stuff online. And again, Joss is going to show you other things that we can use to calculate impulse. But think about this as an energy loss, right? So again, the more static or dynamic friction I have, if it's static friction, remember what static friction is? What's the difference between static and dynamic friction, my friends? You should know this now as you've been here. This is week 13. And you guys should know what the difference between static and dynamic friction is. What is it? If I was going to ask you. Samuel says moving versus non-moving. Absolutely. So static friction is non-moving. So how much energy, how much friction is there when I want to try and get something to move? That's static friction. And dynamic friction is like kinetic friction. It happens when I'm moving. As I'm moving, it's continuing to slow me down, something that's slowing me down. This static friction happens once. Okay, this happens constantly. Dynamic friction. Okay, and bounciness is just the coefficient of restitution. That's what we're talking about here. And that's how you would combine them. So this idea is what I want you to go with. Do I expect you to be as robust as this? No. No, but I want you to try and aim for something like this. Okay. Questions around collision response. We've kind of talked about it a couple of lessons ago, actually. If you think about it, we can extrapolate the stuff that we've talked about with circle responses in 2D, collision response a couple weeks ago. And that same idea with the collision normal and creating something called a collision manifold, that idea of creating a collision manifold is really just all the properties of my collision, right? So you've kind of done a collision manifold. You may have not called it that for assignment number 3, part 1, but you've kind of did it already, right? You just have to add more details to it to make it complete. All right, so that is the lecture slides. What I want to do now is shift gears a little bit and talk about what I've done for you. All right, so I've got this older version of assignment 3, part 2. I'm just going to save it here and put it up on GitHub so you can download it like me. You can have my project. Again, it's nothing different than what we did before, but we've added some things to it. So let me just put this up on GitHub now so you'll have that. So we're going to say view changes. I'll say added sphere movement. It's like a sphere launch is what I've kind of, or sphere behavior is what I've done, right? And I've done that in the game controller and the spheres. I'll talk about that in a bit. So that's what I want to do. I want to push this up to GitHub. So please download this project. It is Game 2005 in the fall 2021 semester, assignment 3, part 2, starter. That's what it is. And where this is I'm going to put it up on your a Blackboard here. Let's add that in. So we'll do a web link for that one. So this is the assignment 3, part 2 starter. Okay, it's like the assignment 3, part 1 starter, but I've added some code for you. And you can ignore it or you can use it. It's really up to you, but I wanted to share it with you. Slide 40, should one of them be addition, not be addition, or be addition, not subtraction? No, slide 40. One things. Nope. No, because remember, it's based on the vector, whatever the vector is. It's always a subtract or an add, doesn't really matter, because at the end of the day, whatever that vector was, it's going to be the opposite. Okay, so, all right, so let's go back to this. So let's open up our starter. Hopefully you've had a chance to download it. It's using the same version of Unity that we've used the entire time. So there's nothing different about it than what we've had before. But I've added a bit of code, and I want to talk about the code I've added in there for us. So what I said was I wanted to add some energy to the sphere. The sphere is going to travel on its own now, right? Right now, it's not using any kind of physics. I'm launching a sphere. I'm not, it's almost like I'm firing a sphere and I'm changing its position. So that's what it's doing right now. In your case, what you want to do is you want to use gravity on the sphere. I'm not doing that because that would give away how to do it. I've done it a very simplistic way. I'm just changing its position every frame. Okay, that's what I'm doing. I've given it a speed value of 20, and I'm giving it a direction vector. That's what all spheres will have now, and I've kind of put that all in each of the prefabs as a demo. Okay, that's one thing I've given you. And let's take a look at that sphere behavior. So what sphere behavior does is it says, very simple, it has two things, speed and direction. Speed is a float, direction is a vector. And then what I'm doing is, let's just get rid of this piece for a second, because we don't need it. Every update, we're going to take the position and add the direction, multiply it by the speed, and we're going to scale it by delta time. Pretty straightforward. So whatever it's going to be the direction, it's going to go in that direction. And it's going to go forever, right? It's not going to stop because we haven't done any collision detection here. This is all you, right? So that's one thing that you'll be doing. All right, the other thing we've done is we also have in a game controller, I've added another script called game controller. Pretty simple. Here's a game controller script. The game controller script has a list of game objects we call sphere prefabs. Okay. And what I'm doing is I've added two little variables here, a frame delay and an offset. Okay. So this is where I'm firing. So really, if I want to, I could put something like a header that says these are my firing properties, or my sphere launch properties, right? And what they do is actually, and I don't need this for now, so I'm going to get rid of it. Remember, whenever we have a mono behavior in Unity to improve performance, get rid of, if you're not using a start or update function, get rid of them, or else it'll slow you down. And then what we're saying is every update, this is kind of one big formula, and I could have probably broken this down a little better, is I'm saying, hey, let's get our fire button, input.getAxis fire button. We can also use getAxis raw if you really want to. GetAxis raw just doesn't have the little nitty gritty stuff from 0 to 1. It just goes either 0 or 1. When I'm pressing it, it's always 1, right? And I also take a look at the time.frame count, and I use the modulus for frame delay. Let's suppose I want to delay 200 frames. When frame count divided by 200 is equal to 0, so I have no remainder every 200 frames, then if both of those two things are true, I'm going to pick a random sphere index. Okay, why is that? Because if I look at the game controller here, here's my game controller, and here's a bunch of spheres I've loaded in here in the sphere prefabs for you, right? And I've said, okay, so pick a random sphere. We can use random.range to do that. Between 0, the index is going to be 0, and the sphere prefabs count. The random range, when you're using an integer, goes from minimum if inclusive to maximum exclusive, which means this part here, it's going to subtract 1 from, which is perfect. It's going to be within the bounds of our index, right? It's not going to go out of bounds for the sphere list, okay? And so we did a random range from 0 to whatever the count is, and then we're going to say, let's make a bullet. We're going to instantiate, use the instantiate keyword to instantiate a sphere prefab. The type that we want is of the random sphere index. So again, one of these. Let's instantiate a new prefab. And we're going to position it where the camera the main camera, which is this main camera transformed up position plus some kind of offset. I'm going to use the camera's transform forward vector, so where the camera's looking, right? And I'm going to multiply by some offset. I'm just using an offset value of 3 here, so 3 units in the direction that the camera is pointing, okay? That's where it's going to start firing from, okay? And then I'm not going to rotate it, so I'm going to use quaternion identity to start off. So the first thing, I just position the sphere. So this makes the sphere and puts it into place, right? Without me needing a sphere spawn point as an example. I'm just making a spawn point, which is just 3 units away from the and you can adjust this if you really want to. You can't, right now what we're doing is you can't visualize what this looks like, and we can definitely improve this by visualization. All right, and then our bullet, we want to take the bullet we just made. Whenever we use the instantiate keyword in Unity, we return a reference to the object we're instantiating. And so now I can say, hey, bullet, I want to get component my sphere behavior. I know that all bullets are spheres because I'm using sphere prefabs, right? So this is safe to do. I'm saying, hey, get the sphere behavior from the bullet and get the direction. Remember, we said that we have a direction vector right here. Get the direction vector and make it equal to the camera main transform forward. That is the direction vector that I'm firing. So I'm firing wherever I'm looking, okay? That's what's happening. And it's going to happen every 200 frames. That's what we should do. Okay, so let's take a look at that. And when we run it, we can move our camera around, and you can play with these values. We can move our camera around, right? And as we move our camera, if I press the left mouse button, you can see that I'm going to get a bunch of spheres firing in the direction I'm looking, right? Makes sense? And we can kind of do this all the time. If you wanted to make it fancy, you want to draw stuff with this thing, that's okay. We can just reduce the frame delay. Let's make the frame delay 1. What if I made the frame delay 1, right? If I did that, and if I ran it, you're going to see that there's no frame delay, right? So if I kind of fire there, you're going to see like a stream of bullets that fire all over the place. I can make a little snake, right? Because that's what's happening here. I'm just making bullets that just keep going forever and ever until they, you know, go away. And they're going to, I mean, it's going to keep calculating forever. That's what Unity will do. Yay, bullets, right? So that's something we can do. We modify the values, these values here. We modify the frame delay. We can do it. I had it set to 200. So we can put that back to that. That seems to be a normal value. We can also play with the offset, but we can do better than this. So we can do better. So this is our start. So hopefully you're with me on this now. Are you with me? Check mark if you've downloaded the project, and if you started off, X if you're not with me, right? So I want to move on from this point. Okay, because this is where I want to start, because if we start from somewhere as opposed to nowhere, and then we can do more. Gal, are you not downloading? Are you watching? Okay, you got a thumbs up. That's fine. So you're saying it's okay. Keep going. All right. And how about the rest of you guys? How about Sophia and Catherine and anybody else? Miguel's watching. Okay, no problem. I'm totally fine with you watching. Again, this is being recorded, so you can always use it later on if you need to. All right, so let's move on. Let's clear all that feedback. Thank you for the feedback. Very nice, very nice. A1 Hack, how you doing? And let's think about now how to make that better. Well, a couple things to do when it comes to the sphere, the game controller. I have these 6 spheres, and they're pretty big. Let's make them different sizes too. So right now we have a rough. They're the exact same spheres every time. They're just the sphere prefab, which is the exact size. So notice the size, if I look at the transform, the size scale is 1. Let's change the local scale from something like 0.1 to maybe 2. Some big spheres, some smaller spheres, and see how that looks like, just to give you a sense of how that works. Now, obviously, you wouldn't want to do this. In fact, what you'd want to do for your game, for your assignment 3, part 2, is you'd want to select you'd have a rigid body component that you'd make your own personal rigid body. You'd attach it to each of these spheres to make them different, right? And you'd probably want to, in addition to that, change the texture so they're not green or blue or whatever, right? And one place that I always get textures is something like, let me just go to the thing here, textures.com. So textures.com is a place where you can get stuff. So textures.com is pretty cool, right? And they have a huge library of textures of different kinds you can download for free, right? They have some limitations on what you can do, but you can choose different kinds of materials, right, that you want to use, right? So they have different things here as well. So there's 3D scans. They've got some really cool content. And we can always search for something like a basketball. So if I want a basketball, that's a basketball net. What about if I want some kind of another surface? Let's say, for example, I want a rough surface, like a rusted wall or something like that. You can see that there's rusted plates, what that would look like, some kind of medieval floor. And these are high definition textures. You don't have to use 8K textures, but you can see what they do. They represent some of this stuff, and you can download some of these things to make your scene more interesting. Okay, so kind of really cool. But this doesn't help us much because this is just, the way it works. I can look at some stuff that we have. For example, I can look at things like, let's look at, metal, and I want to look at metal floors. If I was going to make the metal floor of the what we have inside of our box. Let's say I wanted to make a rusted metal floor, I can choose one of these to download, right? And what I can do is I can just have this pattern go across the floor and we're good to go. We can make a new material and we can add a texture. This is the texture to the material and we're going to have whatever we want, kind of a repeating texture that makes it look pretty good. Okay, so that's what we can do if you wanted to make it more realistic. And it's free. You can log in and register and you can get some free downloads. There's always some free ones every single time. How about a basketball texture? What if I wanted to do that in 3D? So I wanted to get a basketball texture in 3D Unity. How do I wrap this texture around the ball? As an example, let's take a look at some images and let's see if there's something that makes sense. So we don't want this, right? We want something more like this, right? We take an object and we wrap this basketball texture around Unity, right? Notice there's other recommendations as well, right? Here's a beach ball, and here's a 3D map basketball, and so on. And what you want to take a look is, how is this thing going to wrap around this thing? You can also get things like normal maps, so not just the texture, but also the normal map itself, that basically makes the ball feel like it's, or when you look at it, it looks like it has more higher poly count than it actually does, because the sphere right now is perfectly spherical. There's no poly count whatsoever. Really, at the end of the day, it's very low, right? So how do we make this work? So we can find some, a basketball texture that's 3D, and we can say for Unity, right? So 3D Unity, we want to find something like that. And they talk about how to do that. We can go into the basketball texture and open game art, right? We might be able to find something that makes sense, okay? So a dimpled ball, and here's a basketball that I have made for STK to replace the bouncing ball. Special thanks to Charlie who helped me make it. So that is the texture. But does this compute for us when I wrap this around the ball? Does it make sense where I have these areas that are black? As an example, it's a PNG. Let's see what that looks like if I was going to apply it to our code. So I'm going to go to desktop, and I'm going to go to GBC and 2005 and go into here and look at my assets. I have these things and I have a textures folder already. And let's just pull this ball dimpled texture in there just as is. Okay, so it's going to go into our project, right? Awesome, right? Here's our, don't you have to fix the background of the set? Yeah, oh yeah. Oh yeah. Yeah, we have to fix all kinds of stuff. So one thing is, let's make a copy of one of these spheres so we don't mess up, so we can try it out and see what it looks like. So I'm going to take the blue sphere and I'm going to Control D on it. There it is. My blue sphere is now going to be called basketball, right? Basketball. There we go. And the basketball sphere is a prefab. And what we want is a different material. So we have right now a mesh renderer. And the mesh renderer has only one material, which is the blue material. We want the basketball material. Let's make a new material for that. So materials, add it in, create new material. We want to call this the basketball material. And what we want is, we want to get that texture on the albedo channel, right? Some people call it albedo, some people call it albedo, tomato. So what we want is, we want to take this ball dimple texture and put it on the albedo channel. There it is. Take a look at that. And then what we want to do is take that texture or that material and apply it to the sphere. So if I go back to my prefabs and if I go to my basketball, I want to take that basketball material. You can actually search for it by typing in basketball material. You can search for it up here. There it is. And now I have a basketball material. Yay, right? And if I bring the basketball into play, you can see that it looks like a basketball. Nice. Again, not perfect, but who cares? How's that look for you? All right, it looks pretty good. Looks like pretty much of a basketball for me. All right, so yeah, I think so too. So good, we got the basketball. We can use that. And we know We can adjust the sizes and all those things. I'm going to save this. So when I put it up later on, you'll have all these things. So you don't have to do it for yourself. So that's just an example of how I did it, right? What about a bowling ball? Let's get that too. So let's get a bowling ball, right? So again, here you can do a search, right? So if I said, and again, it might not be here, but if I go bowling ball texture, right? We could maybe find one. No, it's bowling pins. So let's take a look at somewhere else. So bowling ball texture 3D Unity. All right, so we want that, and we might be able to find something that has that. Now, Unity also has a bunch of props for bowling already, right? So notice that it also, remember, you can download any assets you want. It has some of these already to use, some red ones. So you can certainly do that. There's also ball sports pack, but you don't want to spend money if you don't need to. In fact, anytime you search for anything on Unity, whenever you do a search like, a ball texture, right? When you do ball textures and you search for it, you always want to look for free, free, right? There's billiard balls. That's not bad. That's not a bad thing to look at as well, but that's not what we asked for. But something like this is good. That's the only one that's available for free. When we say ball textures, right? The ball textures for free. So in Unity right now, there's nothing that I see that is necessarily for free. Also, it depends on how you search. If I said textures, but if I took textures away, then look, there's all kinds of stuff that you can find, like a soccer ball, and you can search through and find other types of balls that are here as well. That might be something you could use. So you don't have to reinvent the wheel if it already exists. But remember, whenever you download something from Unity, make sure, here's a 2D baseball pack. We don't care about 2D, we want 3D, right? So make sure that you have something else. So that's not good. So again, we can say bowling ball, texture, 3D, Unity. Let's go to images now, and let's see if there's something else we can find that's pretty good, right? So there's a beach ball, pool ball texture, so that's cool. And a bowling ball in Blender 3D, cool. In V-Ray, we have other kinds of balls, as an example, but we can probably, looking carefully enough, we can probably over time find something that matches a bowling ball, worst case scenario. And maybe you'll find it faster than me, okay? It's not that difficult to find, as an example, right? You just have to keep on searching. Bowling ball texture 3D, let's take Unity out of there and then see if we can find a better match, right? That's the bowling ball. That's a free Sketchfab model. That's kind of neat. All right, and that's another thing you can do. You can always visit Sketchfab and grab the 3D model. Sometimes they allow you to do that in Sketchfab. Sketchfab is just another application. Sometimes they'll allow you to download it for free, right? So it really depends on the the thing. I think if I'm not wrong, I just need to log in. If I can remember what my login is. It's been a while. I'm not going to remember what it is. Let's just sign in with Google. Sign in with Google. Google. Right, okay. Yeah. Yes. Sure. Yeah. Awesome. And what do I want to do at Sketchfab? I want to purchase or download 3D models from my project. Yay. That's me. And yeah, I can do that. I'm an individual. I can choose my profile, which is a 3D scanning artist of some kind or a game developer. Yay. Okay, good. And sure, I've already done this, by the way, and I'm going to have another thing altogether on here altogether. But yeah, we want to do something like that now. So let's go back. Now that I've got this, let's see if we can do the same thing we did with Sketchfab, right? And we're already logged in, right? So maybe this one will allow us to download. I don't think you can download without. There it is, 3D model. Without downloading, so we can say this is the thing. Here's the attribution if we want to, right? And this is the original full format in Blender. Look at that, the blend file. Yeah, baby, I want that. Let's download that. Let's see what that comes with. So download the Blender file, if it allows me to. Probably did it already, and I'm probably not seeing it. Let's take a look. And yep, it did do it already. So that's me. There's my bowling ball, and I'm going to unzip it, and there it is. And it's a Blender bowling ball. Hopefully, they have the bowling ball itself has the textures. That's what I really want. I really don't care about the bowling ball. I want the textures, right? But let's see what happens when we bring it into Unity. So again, just like we normally do, we can copy this and go into our Unity. So again, it's desktop, GPC 2005 assignment part 2 starter. We'll see what happens. We'll put this in models, right? Because this is a model, and we'll kind of put it in there. And then when we do that, we can go back to our models in Blender. Here it is, and we have a bowling ball. Hey, look at that. We have a bowling ball, and it has a thing. It has the holes in there and everything. All right. Okay, cool. Now for Blender, things to note for Blender. Whenever you pull a model in from Blender in there, I don't need to export it as an FBX. Patrick, it automatically sees it in Unity. But what you need to do here when you click on the model itself, a couple things you want to do. What I like to do for sure is generate a light map UV, right? I definitely want to do that so it looks okay. That's the first thing I want to do. And the other thing that you also want to do, let's apply that. The other thing that you want to do here is, once you've applied that change, is you also want to make it so you have read-write access to the Blender model. So once this is done, you want read-write enabled. That's another thing you want to turn on in a second. And again, I'm okay with you downloading stuff as long as it behaves like a sphere. It doesn't matter what it looks like to me. But hey, this is even better, right? Because it's actually a model that looks like a bowling ball, right? So, so what I want is I want to have my my read-write enabled. Read-write enabled is important because this way I can modify the object. So apply that. And in the top, you can see that we have a couple of options: a rig, if there's a rig, an animation, or a material. Haha. Now, what you can do is you can extract the materials that are used here instead of just having them embedded. So let's do that. We'll say extract materials. We can supply a location for my materials, which will be here in the materials folder. Click select folder. And then once I've done that, I've extracted the materials, then the materials are separate from the model. They're not kind of embedded in the model, which is pretty cool. All right, so that's important to note. All right, cool. So that's my stuff. What does the bowling ball have in it? It has a camera. Oh, that's bad. I don't want a camera. It has an icosphere. That's how it was created. And a point, right? A point light we don't want, as well as the icosphere mesh. This is the icosphere mesh. So we're going to modify this. By the way, let's see if the icosphere actually has holes in it, which is kind of neat. So they've got this. It's probably computationally expensive if you had a lot of bowling balls because of all the detail here, but who cares, right? For us, we don't mind. It's not that many, right? So if we bring this in, we want to make a bowling ball prefab from the model. Okay, so what I want to do is bring this in. Okay, notice it has its own light source. We don't want that. And what I want to do is I want to, go to my prefab and I want to unpack completely. All right, unpack completely. So now I have my bowling ball. I can get rid of the camera that's tied to it. That's part of the Blender thing. I can get rid of the point light as well. And all I have left is this icosphere. Here's my bowling ball. Let's take a look at it. So really, when we think about this, if we bring it closer, we have a bowling ball that looks like a bowling ball. It has a blue material on it, which is kind of neat. But it also has a shape, and the only thing we don't care about this part. This is the containing bowling ball. We care only about the icosphere. So let's bring this out. And we can get rid of the bowling ball parent. We don't need it. Delete. And now we can rename this to bowling ball. Sure. Okay, that's it. And we have a material 1. You could, but then if you did that, then you just have a blue shader. We'll talk about the shader, but the great thing about this is it actually gives us some depth to it. Makes it look like a ball, right? A bowling ball. That's why it's a cool thing to do. It's different than what we did before. You could definitely do it differently, Neil, if you want to. You can get a texture, make your own texture that looks like it's that's got holes in it. Totally fine. It's not like that difficult to do. But we're not in the business of making textures here. Let's go to materials here, where it says material 001. Let's rename this thing to bowling ball material. Okay, and the bowling ball material looks like we have an albedo of a value. That's all that's been done to it. All right, but it also has some additional things. We're going to get to that property. We're going to change the properties in a bit to match all these things in a second, and we can get that information from Blender if you want to go a little bit more detailed than this, if you really want to. And now we have the bowling ball. That's great. And what we can do is inside of the prefabs folder, we can drag and drop this bowling ball. Hello. And we have a brand new prefab that we can use as many times as I want. One thing that we want for both the basketball and the bowling ball, the basketball has sphere behavior, but the bowling ball does not. Okay, and it's not very shiny either. We want to make this bowling ball shiny, like what we saw inside of our inside here. We want to make it look like this. So we want to give it a specularity that makes it kind of shiny like this. There's a lot of other things you can do too to do that. Make it the material so it looks like it's a little bit more shiny. You can make it black instead of blue. You can do a lot of stuff. But for me, I mean, I was pretty lazy when I did this, so I don't care. Let's go and modify it in Unity, right? Because you don't care about that. So first, let's add in the component that we want, which is the sphere behavior, because that's what it's going to be. And we can still add the speed, which I think is 20, I think is what I said, right? So again, you can modify these. You can also add in your own behavior that you want and so on. Okay, so I'm just using this as an example. There's my bowling ball, right? And let's take a look at the material for a second to make it look more realistic. So again, if I was going to look at the bowling ball material, you can see that I have albedo, but I don't have a metallic value or a smoothness. And let's see what happens if I was to change these values here, right? So if I said something like, well, I want to add a metallic value, right? And you can see the effect of that. I want to increase the metallic value. Or I want to change the smoothness of the ball to make it look like it's a bowling ball. So that looks like it's a little better. You can see that the source is metallic alpha, so it looks like a bowling ball, right? Something like 0.65 looks about right, okay? So you can make it look like that. If you really want it, you can make it even glow by adding an emission property. Not going to do that. All right, so that's something that you can change. If you don't like this, you can always change from a standard shader to a standard with specular setup. And sometimes I find that this is a little bit nicer because then you can also have a specular color like a shine. What's the shiny color that you want? And you can choose what that shiny color is by adjusting the overall shininess to it. So I can make it kind of really shiny or not, right? So I kind of like specular setup in many ways more. I can adjust the smoothness as well to make it more blunt or more shiny the way I want it. I think this is good for me. And now this gives us kind of a sense of a depth for the handles. So it looks way better than it would have been if it was just a simple texture. All right, and if we had a normal map, we can add a normal map. We don't have that, but we can always generate one if we really wanted to. Okay, cool. This is my bowling ball. I'm good, and I've got that too. So what if I wanted to use that in my sphere caster that I have? Because I have a sphere caster that's in my game controller. I have a bunch of these spheres. They're all spheres too. I know that because I've just called them spheres. But let's add the basketball, right? I want to add the basketball here as well. So a couple ways to do the basketball, because the basketball is still a object. We can add a space for it on the bottom, and we can just drag and drop the basketball itself from the prefabs model in here. So you can say basketball, yay. Or I can take the bowling ball, let's say next, and I can drag and drop it on top of there where the name of the thing is, and it automatically add that in there as well. So now basketball and bowling ball are also there. Yay, right, for testing. All right, see what that looks like now when I cast stuff out of it. Can I get the basketball, please? Yay, I got some basketballs, and that's pretty good. There's a bowling ball occasionally, right? And they're going to go forever. All right, so we can replace some of these if you don't like them. If you only want the ones that we have, let's get one more. Let's get the baseball and see if we can get a baseball texture. And that'll be it for the textures part. So again, I want to look for baseball texture and 3D Unity, all right? And again, it says baseball essentials, but I have to pay. I don't feel like paying. I'm going to go to images. Hey, that looks pretty good, you know, from DeviantArt. There's also one from Sketchfab. If I want to grab an actual baseball with some like physical texture on it, you know, so there's a lot of options here. There's also a baseball texture normal map, so we can add the baseball texture on there. I wonder if this one has both the texture and the normal map that's available to us. Sometimes when you go to Filter Forge, you might be able to find something like this as well. Okay, so that's something that you can find. Let's continue looking because I don't like that. But this looks like what we want, something that looks like this, right? It looks like it's going to be white like this, and it's going to, you know, kind of stretch on top of our ball. No problem. And again, we want to look for something that makes the most sense, right? Where we map that onto our ball, okay? Barring that, we're just going to go right back to Sketchfab and download that one from Sketchfab and see what it gives us. So this is kind of a dirty looking ball from Sketchfab. Ooh, it even looks like it has some nicks and stuff on it. Let's go there. We know we're logged into Sketchfab, and there's the ball. Looks pretty good. Really, really realistic, right? You don't have to go so realistic. And what about if I want to download the 3D model? What versions do they have it? They have it in FBX, GLTF, and as well as an augmented reality format. Let's just get the original FBX version this time and download it. And now what I'm going to do is just the same as I did before. I'm going to grab that from my downloads folder. So there's the, when it's finished downloading, here it is. Worn baseball, yay. And I want to unzip it. Cool. And inside the worn baseball, it has two things. It has the source, the FBX, plus the textures. Awesome. Look at that. Look at that texture that it has, right? So I can actually just maybe grab those textures because we don't care about what it actually looks like. Let's see if we try this first without the FBX, right? Because I mean, I'm guessing that they're not going to be anything if you have a normal map like this. So let's grab these textures, right? And I'm going to grab those and put them inside of, you know, the thing there. So I'm going to go into desktop GPC, GAME2005, and inside this one, and go into assets, textures, and fire them in there. Baseball, all right? Now there's a bunch of different things here. The textures are a normal map, right? We have a bunch of other ones in here as well, right? What could these things be? Normal map, we know what it is, right? What else? What other textures do you think the C is and the O is and the R is? What are those textures? Well, you can actually see them, right? So if I go back to where I was, which is in the textures where I got them from the textures, these ones, which one do you think is the regular texture? Probably this one, right? The O, right? We need these two for sure. And there's this one and this one, okay? So there's the R and there's the C, okay? We don't know what they are, but we want to know what, if we're going to guess what they are. You know, first of all, you can also look at his instructions or directions to see what they are. Sometimes they mention what kind of textures they have, the textures they have as well. But we don't care. Let's try and use those in Unity now for the baseball. I'm going to make a copy of the basketball. And we're going to call this prefab baseball. And all I want to do with this one is change the material. So we're going to make a baseball material. So new material, I'm going to call this baseball. And inside the baseball material, we're going to just add some of those things in here. Now, there's a normal map, a height map, and let's see if I can change this to standard. What do I get? I get a normal map, a height map, an occlusion map, which is interesting, and a detail mask. Okay, so those are the things. I got an albedo, specular, and so on. The other one you might also want to try if you're taking something right from Blender is Autodesk Interactive, which gives you a very close approximation of a principal BSDF, right, shader type that you can bring in. Okay, so that's what you can do here. So we have a roughness right, which is kind of neat. That's an R. We have a normal map, and we have an albedo, right? So let's see if we can bring some of those textures in and see what happens. So maybe that's roughness that we have here. So O would be your albedo. There's the stuff that you have here, right? You can also try O as the occlusion map. You could try that as well, right? So if we take that off, we can reduce that and see what that looks like. We can go with the R which is the roughness. We can kind of add roughness to this thing, right? We can go with the N, which is the normal map, right? So that's the normal map right there, right? So see what that looks like. Okay, not quite mapping properly, in my opinion. And you know why this is not quite mapping properly? Because the reason why we want to use the FBX on this one instead of this is because when we try it this way directly, we can see that the way that this has been, the vertices have been unwrapped, right? Or the basically the way the UV map has been unwrapped, it's not correct because it's a regular sphere that we're using. So nice try, Tom, but it didn't work. Let's bring in that FBX now, right? Because I didn't want to, but hey, what the heck? Who cares? So again, let's get rid of that prefab. So prefab baseball, goodbye, because that's not going to work. And instead of, we'll do that, we'll bring in that FBX. So that is inside of sources. So FBX, let's drag and drop that inside of the models folder. And let's see what we get for that. There we go. Baseball.fbx. It's got a little bit of form to it. That's why it's the way it was, right? Round ball. Oh, it's pretty good. And what we have is, from a materials perspective, we don't have any materials added onto it, right? So again, we can extract materials if we need to, right? So I'm going to extract materials, and I'm going to go to Assets, Materials, and we're going to call this the baseball material. Select folder. Eventually, we're going to call it that. And let's bring the baseball in to the scene to see what it looks like, right? So we can see that it's kind of warped. And can we even see it? How small is this thing, right? We may have to make it larger as well. Closer to our camera. Like right close to us. Yay. Okay. That's so interesting. Is this disappearing? Is it because of my camera? Huh. I'm using Lambert material. Okay, what is the Lambert material anyway? Okay, so this is where we have a standard material that it's using. It's just, they're calling it Lambert. All right, but now let's see if we can apply those textures as well. And that's curious that it did that, though. I didn't like the fact that it did that, and probably because, let's get rid of that again. Probably because in the models, whenever we bring in a model, guys, remember I said that in the models folder, you want to kind of spark up your light map UVs. You want to do that, and you also want to have access to your read-write. It's important to do that. So sometimes there's other optimizations you can make here as well. Let's just call this baseball before I time out for today. And let's put that into play, and let's let us reset it and bring it up so we can see it. It looks like it's like super small. Yeah, like super, super small. Let's make it like 10 times bigger so we can see it. There we go. I was getting worried. I was like, what the heck? Like, we can't see this thing. This is really tiny. That's why. All right. There we go. Okay, that makes me feel more comfortable so I can actually see what this thing looks like. All right, so now let's try it again. So in the materials, we can see that we have a Lambert material that we have on it, and we can take in the textures that we have, which is the baseball and the normal. Let's put the normal map on now, see what that looks like. Now that already looks better, right? So again, if you look at the normal map, oops, you look at the normal map for the ball, it looks already better than what it did. Right, that's how it looks now, right? So pretty good. Let's keep going with that. So from a textures perspective, materials perspective. Let's go back to Lambert. And now that we have our material, let's keep on with the other stuff, right? So we have a C value, right? And an occlusion value. Let's see what happens when we add the occlusion value in there, right? So that's pretty cool. Roughness value, we don't have a roughness value here. That means I have to switch shaders. I told you, it's probably Autodesk Interactive. That looks starting to look much better, actually. And it's a little shiny from my taste, but that's just me, right? So we're going to try and figure this out. Here's our roughness value. So we have a roughness that we're going to have in there. And what are we missing here? Some kind of, I wonder if the occlusion also works nicely with our material. Again, you might try different options here as well if you download something that is very normal. It's not bad. Like, it looks like a baseball. Might be color. Let's see if that's true. If C was color, then it would color the ball. Yeah, that's pretty good. Thank you. C is color. It makes it ugly, but it's a scuffed up ball anyway. That's what we know, right? It's a scuffed up ball. So nice. It looks way better than we would normally make it, but it's pretty small still, right? Like, I mean, it's like, it is what it is. So I can take that baseball and I can make it into a prefab. All right, so here's my prefab. Let's take this thing and drag and drop it in. It's going to ask me, do I want to make a variant? I want to make it an original prefab. So it's going to be something separate from the other thing. Okay, that's what that is. Here's my baseball. And the only thing I want to change is the material. So the material was Lambert. That doesn't make any sense. So let's get rid of baseball material, which is what we had. Probably could have worked with that one too. And let's make this the baseball material. So baseball material. Okay, baseball material. It says the material used texture is a normal map. Let's fix it. Yes, fix it for sure, because that'll make it even better than what it's supposed to do. Looks really good, much better than before. All right, a little bit small though. So we'll see what it looks like when it's far away, and if it's too small, we'll make it a little bigger. But that's the baseball. Yay, awesome. Okay, so now that we have a prefab that's the baseball, we can go to our controller and we can just drag and drop that baseball there as well. And I've done some of them. There's a ping pong ball you can use as well. And if you want to, you can also get rid of these ones. If I don't want to use the spheres anymore, right, as an example, I can delete them, right? So I can delete all the ones I don't want to use, and I can just use the ones that we made: basketball, bowling ball, baseball, right? And let's see how that looks when I use those things. So first of all, let's go back to our baseball for a second. Baseball, one thing we're missing is it does not have a component. Sorry, I forgot to add the script, which is my sphere behavior, which we want to add in there. We want to add a speed of 20. Again, you can modify these things. I'm not going to modify them for you. And maybe you can add a rigid body here instead, right? And then we're going to be able to cast that according to what we want to do. So again, now if I kind of cast it, you're going to see that there's different sizes. I got basketballs which look really large, maybe too large, and baseballs that look very small. And what you want to do is you want to size these things correctly, right? So that's what you want to do. Okay. Basketball, I think the baseball looks even too small as it is. Like, it's much smaller than it should be. So let's make it even double the size that it was. Let's just say that all baseballs are bigger. I mean, again, it's up to you, you know, how you want to do it. I'm going to go to the prefab here to do that. And you can have the original model there. I've left it there. That's why I make a copy of it, because instead of doing it like that, then I can make it so that it is 20 times larger. Yeah. Let's see what that looks like. And then we'll do one last thing before we go. So cool. Yeah, that's a little better, right? So ball, and we can see that we can cast the thing wherever we want to, right? And that's pretty cool. Okay, now one thing that helps a lot is if we have a reticle, and we can do that by adding it into the canvas. That's a really dumb thing to do. So in the canvas, right, we have our panel which is hidden. We can bring up that panel anywhere, anytime we want. But in the canvas instead, I want a reticle to be a text object. So again, I can use whatever I want. So if I want to use a UI text object, they didn't add Text Mesh Pro, we won't add that in. Let's get rid of that, delete. Let's do that again. So add in a UI text object, and we'll call this the Reticle, right? I think I spelled it right. And then what you want is a little thing that looks like this, right? Which is the a little marker, right? But it has to look right. And instead of it being black, we're going to make it white, right? And we want to find this in the canvas. The canvas is a screen space overlay, which is good, right? So where is this reticle? Well, if I look at the 2D map, the reticle appears to be way over here, right? So that's pretty small, and it's sitting right here. Let's make it so that it's bigger, and let's make it so that it's centered and centered right in the screen. We want to make it so that the center, the anchor is preset to the center as well. And let's go back to the 3D view and go back to my box, right? Because that's going to give us kind of the right view. And now when I run the game, theoretically, we should see a reticle that's in front of us, which is a cheap approximation of where everything is. This is the center of the screen, and you can see that that is where we're firing our balls. Okay, wherever my reticle is, that's where I'm firing. That makes sense? No. Neural maps do nothing. Remember that that the neural maps are just the way that the color hits the sphere, right? So the lights, how the lights affect the sphere, and how when we light something up, when we visualize something or we draw it, what we're saying is we have a very low poly object, which is probably just a regular sphere. And what we're doing with the normal map is we're adding false detail. That's what we're doing, right? Because that's what the normal map does. It's not true. So it's not going to affect anything other than the way that it looks. And of course, you probably would wrap a sphere collider of your own around it. So who cares? Once you wrap a sphere collider, it doesn't really matter what you have. One thing to check also is make sure that by accident, I didn't put a sphere on anything. So make sure there's no collision systems on the baseball, on the basketball, or on the bowling ball by accident. I don't want to put anything in there. That would mess you up. Okay, so it looks like there's not. You still need to get the ping pong ball, and there's other ones, but I've given you a few tools to make it okay, at least to start you thinking along the lines of that. The other thing you might want to think about is the crates or boxes that you're going to have in here, and you would probably start stacking them in a particular order, and I'd leave you to do that on your own. Okay, let's end this. So file, save. We'll give you all this stuff. File, save project. Just to give you a head start on some of this stuff. Again, for the most part, it's very basic, but at least it gives you somewhere to start as opposed to normal. All right, so let's go exit and let's put this up on GitHub. So we'll say we added a bunch of different things. So I found them for you. So we say added basketball, bowling ball, and baseball. That's what I really did, right? And then let's push this up to GitHub. Okay, so you should have all that. If you download the project that I have, that I've been using, you can always download that and you'll have everything that I have. Questions around the project and how to start? There's way more things we can do here in Unity. And like I said, Sketchfab is your friend. You can find a lot of images here. I'm sure if you search for ping pong ball, right, you can find all kinds of stuff, right, that maybe is going to have what you need to grab that. There we go. So we have a ping pong ball there, and you can always test to see what it looks like. So if I kind of go in there and you want to see the model, it's free to sign up, and you can see it has a bit of scuffing and stuff like that too. It looks like just a white little sphere, and that's fine. For the most part, it's like very basic. Okay, it's not, I mean, it doesn't really look like much. You can actually just make a sphere, right, that's white and that's small enough. As long as it looks like a ping pong ball, then you're pretty good. I pushed. Yeah, so if you look at my Get Kraken, I pushed everything. Right? Or maybe I didn't. Aha. Good on you. And one day when it feels like pushing, it'll do the thing, right? It's not. And this is where, sometimes I find that, it's working, and it's not updating. And it bothers me how long it takes sometimes to get Kraken when I can do it in a command line in 2 seconds. All right, so now you should be up to date. All right, questions before we end for the day. So some really cool stuff. I'll give you Sketchfab as a link for some places you get models as well. A lot of times they're free, so that's good. We saw that, and let's do that here. So I'm going to say build. We'll add a web link for Sketchfab. Okay, Sketchfab link. It's a free sign up. Anything else? All right, guys. Could you switch Mohammed from? Oh, sorry. Oh, yeah. Yeah, I could do that. Okay, Sam. No problem. Stick around, and I'll do that after the thing. Okay. No problem. All right, that's it. I'm going to. How does it compare to GitHub Desktop? I like it more because it's more visual. No problem. Thank you. All right, and I'll stop recording this now. All right, there you go. That is that. And